Yeah. Sounds good. Thank you.
So the next speaker is Colin Desmarais from TU Wien, Austria, and he will talk about the depth in random recursive metric spaces.
All right, great. Thank you. I guess that's the intro slide. Sorry about that. Great. So as a little refresher, I'm sure most people in the room know what random recursive trees are, but very quickly, we randomly and recursively construct some trees. We start with T1, which will consist of a single vertex with a root for all subsequent trees, which we label V1. And at each step, we select a vertex uniformly at random and add a child labeled Vn. So only one choice to make here, add a child labeled V2. At this step, we have two vertices in the tree. We select one at random with probability 1/2. Let's say it's V1 and add V3 and continue for as long as we want. And we can ask the question, well, what's the distance from Vn to our root V1? This is the insertion depth. And this was answered or studied by Luc in 1988, who proved a central limit theorem. Now, people have looked at different types of similar models of increasing trees. For example, you could select vertices proportional to an assigned weight to each vertex. We could select vertices at each step proportional to the number of children of the vertex. Those are preferential attachment trees. Initially, a few years ago, myself and Hassan Mahmoud had looked at a model called hooking networks, where we were attaching graphs at each step. And under some conditions, we were able to prove a central limit theorem. The under some conditions really annoyed me. I wanted to get rid of them. Once I had gotten rid of those conditions, then I asked, well, how far can we generalize these models and still prove a central limit theorem for the insertion depth? And that's why I apologize for the next 2 slides of complicated notation. So instead of attaching an edge and a vertex at each step, let's look at what I call blocks. These are weighted hooked metric measure spaces. B and D is a complete separable metric space. We identify a point in the metric space, which we call a hook. We also assign a probability measure on the space B, and to each block we assign a weight, which is a non-negative real value W. Of course, let's make this random. So suppose I define a random weighted hooked metric space. I'll just call it blocks from now on. I'm not going to get into why this is well defined and you can do this, but just trust me for now. So for n equals 1, 2, 3, 4, 5, we sample IID blocks Bn with the same distribution B, and we initiate with some block that might have a different distribution, but we condition that the weight of the initial block is strictly positive. It may have the same distribution as B, it may have its own. Yeah. Okay. Bit more notation. So I'm going to define this delta n prime. This is the distance from the labeled point Hn prime in my block Bn to some point U selected at random using the probability measure Pn prime. So I sample a block, I sample a point within that block according to its probability measure Pn prime, and I look at that distance within that metric space. That's my delta n prime. So for n greater than or equal to 1, all of these delta n primes are IID distributed as some delta prime. And of course, all of the weights Wn for n greater than or equal to 1 are IID distributed. And I just want to note here that these are not necessarily independent, right? I sample a space according to some joint probability measure. So, okay, so what do I do with these blocks? Well, we recursively construct a random recursive metric space. So again, this consists of a 5-tuple with some space, a metric on that space, an identified point, which I'll call the master hook, probability measure on the space, and a weight to the random recursive metric space. We initiate by setting G0 equal to our initial block B0. The identified hook of B0 becomes the master hook, acts sort of like the root in a random recursive tree. At each step, we attach our new block by doing the following. We select a point Ln according to the probability measure on the space Gn. We glue together the identified hook of our new block with this latch that we've chosen. Concatenate the metrics. Since we've just taken two metric spaces and joined them at one point, we can define a new metric on the whole space. Add the weight of the new block to the weight of our random recursive metric space. And then we have here, this is a weighted probability on the whole space. So essentially, with probability Sn over Sn plus 1, we select a point. So for the next latch, with probability Sn over Sn plus 1, we select a point in the old random recursive metric space. And with probability Wn plus 1 over n plus 1, we select a point within the new block that we've attached. So I'm just joining the two probability measures in this weighted fashion. Okay, so I just want to point out that this is similar to models of decorations on trees, specifically a few papers by Senizerguez, but I want to point out the difference here that I have not assumed any compactness of my metric spaces. Just as before, I'm just going to define the space now in my large space from the master hook to the latch I've attached at step n. And condition on some second moment conditions here. We have a central limit theorem with the parameters given here for the expected value and the variance. So this is the main result. Okay, 5 minutes left. So an application, random trees, sort of see how this looks, right? So as I said before, if I take a random recursive tree, but now at each time that I attach a new vertex, I assign it a weight, and now I could select vertices proportional to that weight. These are weighted recursive trees. As a generalization, could take this further, select vertices proportional to some parameter times the number of children plus that assigned weight. These are preferential attachment trees with additive fitness. We could go further, add lengths to the edges above the new vertices we've attached. So these would be preferential attachment trees with additive fitness in random environments. So putting all of these together, I mean, these are sort of separate generalizations that people have looked at and examined the depth. But with this model, we get to sort of put it all together into one tree. As a random recursive metric space, I don't have much time, so I've just sort of defined what the blocks here would be, but maybe this is better with a picture. So my root vertex is just essentially a block consisting of just a single point. At the next step, I attach a vertex. So I've attached this block in blue here. And now at the following step, when it comes to selecting a vertex, right, I can select V0 with probability proportional to alpha plus its weight A0. Alpha due to the fact that it has one child. Or I could select vertex V1 with probability just proportional to its weight A1. And in the context of random recursive metric spaces, this is equivalent to, well, either I select the block, this red block here, with probability proportional to A0. Or I could select V0 by first selecting the blue block with probability proportional to alpha plus A1, and then within that block, selecting the hook here with probability proportional to alpha over alpha plus A1. In that case, adding those probabilities together gives me alpha plus A0 over S1. Hopefully that makes a bit of sense. If I continue this process, let's say I've selected V0, or specifically I've selected the block, the red block, and attached a new block. This is green, supposed to be green. So once more, by attaching this hook, I've added to the weight of the vertex V0, or equivalently, at the next step, I could either, there's the probability that I select the red block, or that I select one of the two other blocks and within those blocks, select the hook to attach the next block. Okay. So this theorem from earlier, I can then derive that if I have these conditions on the weights of the vertices and the lengths of the edges, then the insertion depth follows this central limit theorem. So this is just a way of generalizing several results on the insertion depths of random trees all into one big theorem. Okay, maybe I can quickly go through the proof outline. It's very, very brief, I promise. So in the case of random recursive trees, the way you can prove the central limit theorem, define a random variable y and k, which is equal to 1 if the vertex vk is on the path from the root to the vertex vn and 0 otherwise. Then if I sum all of these up, I'll just get the depth of the nth vertex. We can show that each of these is an independent Bernoulli random variable with parameter 1 over k, and so we can just apply standard central limit theorem to prove central limit theorem for the insertion depth. In our case, we follow something quite similar. So here I define, this is the probability that the path from the master hook to the latch that I've selected goes through the block k. So this is its Bernoulli random variable parameterized by its weight over the total weight at time k. And then this, if you recall, this delta prime was the a random distance within that block. So this is essentially where I would have attached the new block. So if I just say, well, what's the probability the path goes through the block k and then multiplied times the distance that path would have taken within that block, add those, multiply those two together. This gives me the depth. Once more. So if I condition on my sequence of blocks, these random variables are independent, but that's only if I condition on the block, so I can't necessarily use a central limit theorem. But I can define some martingales. One of them is a square integrable martingale, and I can use martingale central limit theorem to prove the result that I need. And that's it.